Basically, Git is just a small key value store plus a few pointers. Today, we are going to dive straight into that data model, and once you see it, every command will start to make sense. Everything Git knows about your project is stored in a hidden directory called .git. If you delete that folder, Git simply stops tracking your files and your whole project history just disappears. If you look inside that directory, you will find four main things: an objects folder, a refs folder, a file called head, and a file called index. These four things create the entire system. As I mentioned at the beginning, Git is simply a key value store. You hand it some content and it gives you back a 40-character hash. That hash becomes a key you use to retrieve your data later. Because the key is generated directly from the data itself, we call this a content addressable storage. We can prove it using plumbing commands, which are the low-level tools Git uses behind the scenes. If you pass a string to the git hash object command, Git compresses it and saves it straight into the objects directory. It returns the hash, and if you give that hash to the git catfile command, you get back the exact same data you saved. Content addressing gives Git two main advantages. First, it stores identical content exactly once. If you have 10 identical files in different directories, they all produce the same hash, so Git only saves one copy. The second advantage is that Git catches data corruption instantly. If a single bit flips on your hard drive, the hash no longer matches the content and Git knows right away. Git uses three main object types to build your repository. Technically, there's a fourth one called the tag object, but since it only puts labels on commits, we can skip it today. The first one is the blob, and it stores the raw contents of a file and nothing else. It has no file name, no file path, and no timestamps. It's just the raw bytes of your code. But this creates a problem. If blobs are completely anonymous, how does Git know which hash belongs to which file? Git solves this missing context with a second object type called a tree. A tree is Git's version of a directory. Its only job is to map file names back to those anonymous blob hashes. If you inspect a tree object, it reads like a simple list. Every line follows exactly the same pattern. It starts with the file mode, followed by the object type, which in this case is a blob. Next comes a hash, and at the very end of the line, you can see the actual file name. This is how Git finally connects a name to your raw data. But repositories are not just flat lists of files. You usually have folders inside folders. Git handles this by letting a tree point to another tree. If there is a subdirectory in your project, the tree adds a line for it. The structure stays the same, but the object type changes from blob to tree, and the hash now points to that nested tree instead of a file. By linking trees to trees, Git builds the exact directory structure of your project. A single root tree describes the complete state of your project at a specific moment in time. It defines the exact hierarchy of files and folders. But the tree tells us nothing about when this state existed, who created it, or what came before it. So Git records history with the commit object. It is just a tiny text file, but if you inspect it, you see exactly what Git uses to build the graph. The first line starts with tree, followed by the root tree hash. The second line starts with parent, followed by the previous commit hash. After that, it records the author, committer, and a timestamp. Finally, at the end of the file, you get your actual commit message. The parent pointers chain these commit objects together into a directed acyclic graph. That graph is your project history. Every commit points backward to the commit that preceded it. Since every commit contains the hash of its parent, changing anything in the past changes every hash after it. This Merkle-style structure is the same idea that blockchains are built on. You cannot modify an old commit without rewriting everything that comes after it, because the new hashes cascade all the way down the graph. We usually assume a commit just stores what changed since the last one. We think of version control as a stack of patches, but it does not work that way. Every single commit points to a full snapshot of your entire project. When you run git diff or check a pull request on GitHub, you are looking at line-by-line changes. But Git does not store those diffs anywhere. It calculates them on the fly by grabbing two trees and comparing their hashes. Storing a full snapshot for every commit sounds extremely inefficient, but unchanged files produce the exact same hash. A new commit simply reuses almost everything from the previous one because the new root tree just points back to the existing blobs. To clean up the rest of the redundant data, Git runs garbage collection automatically whenever your repository grows past certain thresholds. It compresses loose objects into pack files and saves similar objects as deltas to save disk space. So diffs actually do exist, but they are strictly a storage trick. They remain completely invisible to the core data model. Once you see how commits work, branches start to look completely different. We usually treat branches as heavy, parallel timelines. But in Git, a branch is literally just a 41-byte text file sitting in the heads directory. It contains exactly one thing, a single commit hash followed by a new line character. That is the entire implementation of a branch. If branches are just text files, how does Git know which one is active? Every project has one file called head, which basically controls what you see in your working directory. It simply holds the path to your current branch, and that branch file points to a commit hash. When you create a new commit, Git saves a new commit object in the objects folder. Then it reads head file to see which branch you are on. It opens that branch text file and replaces the old hash with your new commit hash. Basically, that's how a branch moves forward. Let's take a look at another example, which is merging. Say you merge a feature branch into main and nobody has added any new commits to main while you are working. In that case, Git can do a fast forward merge and it does not create a single new object. Git just opens the feature branch text file and copies the commit hash. Then it overwrites the hash inside your main branch text file. The pointer slides forward, Git checks that state out into your working directory, and the merge is complete. But what if someone did push new commits to main in the meantime? Now, the two histories have diverged, so there is no straight line for the pointer to slide along, and a fast forward is impossible. So Git performs a real merge instead. It finds the common ancestor of both branches, combines the two snapshots, and creates a brand new merge commit. And that merge commit is special in exactly one way. It has two parent lines instead of one. Only then does Git move your main branch pointer to this new commit. Sometimes you check out a specific commit instead of a branch. In that case, Git updates head to point directly to that raw commit hash. That's called the detached head state. You're operating without a branch pointer, and if you make a new commit, Git will update the head file. Between your working directory and your permanent history sits the index. It is just a single binary file. This file acts as your staging area, holding the exact list of everything your next commit will contain. When you run git add, Git immediately hashes your file. It creates a new blob and writes the raw bytes straight into the objects directory. Then it updates the index file to connect your file path with that new hash. Then when you run git commit, Git reads the index and then converts your staged entries into tree objects and saves them straight into the objects directory. Then it wraps a new commit object around that root tree and links it back to your current commit. The last step is just a pointer update. Git reads head and moves your branch forward. Once you see the objects and the pointers, the commands finally start to make sense. Let's look at a common command like git reset. You are simply moving the current branch pointer to another commit, usually an older one. The flags you pass just dictate what happens to your actual files. Running git reset soft moves the pointer but leaves your index and working directory alone. The mixed option moves the pointer and updates the index. And git reset hard moves the pointer, syncs the index, and completely wipes your uncommitted changes in tracked files. Untracked files survive even a hard reset. Another example is git rebase. The name implies you are moving commits around the graph.